So it turns out
Whoa.
drones are pretty complicated. They have very cool tech bolted down to carbon fiber drone frames. But all I have are 3 years worth of spare parts that I need to get rid of. I typed all of these spare parts into a website to decide what projects I can make with them, and the most advanced one was a drone. Well, I guess I'm just gonna have to sit in a cave and somehow make a precision machine with a box of scraps. I have a few tricks up my sleeve, which I think I can use to make this work. That, or I'm probably just in over my head. This is a PCB, and it's essentially a tiny metal board that connects all of the necessary electronic components together using tiny embedded wires inside of the board. And for drones, that's very important. Unfortunately, I don't have a spare PCB that is custom made specifically for this project. So what I'm gonna have to do, if I want to only use spare parts, is to use a perf board. And what a perf board is, I mean, it kind of looks like a PCB, but you essentially put the components on top, and then you have to manually solder the connections between the components together. Soldering being melting metal so that parts can bond together to like a wire, and then the wire bonds to another component so that you can connect components together. Many drones use a microcontroller to control motors and sensors. In other words, it's the brain of the drone. The ESP32 is the best one that I have from my spare parts bin, which is very fortunate because it's a pretty good microcontroller. And I also used it in my most recent drone, and it flew okay. It was able to hover, in other words. Other microcontrollers I had was an Arduino Nano IoT, which is the same kind that I used on my first ever drone, which failed, and an Arduino Nano non-IoT, which is even worse than the IoT version. ESP32s are usually not used for drone flight controllers, so I will need to squeeze as much as I can from this microcontroller and get the most performance. Alright, so drones are impossible without this thing. An inertial measurement unit, which is a mouthful, so I'm just going to say IMU. Fortunately, I got 2 of these in my spare parts, but unfortunately, they're deemed obsolete by the manufacturer. There is hope though, because this IMU, it's called an MPU 6050, is actually used in commercial flight controllers, like for drones. So we can still use it if we program it right. Now the cool thing about IMUs is that it can allow the drone to feel how much it's tilted, as well as how fast it's spinning. And it's similar to what we have in our ears. It's called the vestibular system, I think. I don't know, I just Googled it and Gemini said it's vestibular. I'm not a biologist, okay? Anyways, there's like water in your ears, apparently, and if you start moving, or if you're tilted to some degree, then the water in your ears will move around and you will be able to feel that. Sort of like, I guess, a bubble leveler. When you tilt the bubble leveler, the bubble moves, and yeah, you could see it. You could see it level. That's basically the point I'm making here. How does it relate to IMUs? IMUs have the same thing, except they don't use water. They use a spring mass system. So it's just like a weight, and there's some springs attached. And whenever we move around, guess what? The spring and mass system moves around as well. If we lurch to one side, the spring mass system will kind of lurch to the other because of inertia, and then IMU can detect that. Now what I'm doing here is I'm mounting the MPU 6050 IMU right underneath where the ESP32 microcontroller would be, and this would save a lot of weight. Alright, so the magical IMU with its spring mass fancy schmancy system is able to allow the drone to feel how much it's tilted and how fast it's tilting. But the motors can actually act on it. To power these motors, they connect to these MOSFETs. It's a very long name. It's metal oxide semiconductor field effect transistor. They are electronic switches that turn on whenever the microcontroller gives the signal. And then that will allow the current to run through the MOSFET and the motor because they're connected together. And that spins the motor. And then we go up, hopefully not down. Now, I added some extra stuff to this MOSFET, and it's called a gate driver to turn on a MOSFET, which turns on a motor. And the reason why we do that is for efficiency and responsiveness, because this gate driver allows the MOSFET to turn on really fast or turn off really fast. It's just that the only gate driver that I could use was very hard to solder. I mean, it's a very small thing, and I had to solder individual wires to it so that it can actually sort of adapt into the holes of the perf board. And on top of that, I actually had to be creative with how I used the gate driver. Typically, you would use this whenever you have two MOSFETs connected together, but I need them to be separate. Now, fortunately, this gate driver has pretty much the same exact thing on the top as it does on the bottom, so I just use the top and the bottom separately. Alright, so you know that thing about the gate drivers and how I used it because it's a fancy efficiency gain and responsiveness gain? Well, it turns out it doesn't work with the LiPo batteries that I will need to use. Problem is, it's 4.2 volts, and the gate drivers only work at 8 volts or more. I made the tough decision, probably an idiotic one, and that is to add a very bulky boost converter that turns 4.2 volts into 10 volts. The only ones that I had in my spare parts bin were very heavy relative to the drone's total weight, and it's 10 grams, which is a lot for a tiny drone like the one that I have to make. I'd like to introduce you all to the flight controller from hell. Because, I mean, this is probably, I mean, not the worst thing that I've ever made, but the most unreliable thing that will be put on a flying object that I've made. Okay, now I'm gonna need a frame, but I can't 3D print it because I decided to be crazy and make this drone project even harder. Fortunately, I looked around my room and I have a lot of cardboard boxes around. And yes, I am going to use cardboard to try and make this drone work. So I start by cutting the outline. If we're gonna use cardboard, right, might as well make a nice little outline that is very precise. I mean, it's just a very simple frame for ease of cutting with some holes for the perf board bolts and some holes for the motor wires. We got this, right? Would they be rigid enough? Okay, so cardboard wasn't a good idea. I don't know why I thought it was, but I had a brilliant idea. All right, what if you use plastic fork handles? Our savior. Because fork handles are very stiff, right? So I just used it to reinforce the drone frame and hot glued it. And then try and get the other one. That is really close, jeez. Oh geez, there's gonna be wires everywhere. So some of these parts that I've used in this drone are from the first ever drone that I've ever made. Not exactly the exact same parts, but the same types. And with this cardboard frame, it doesn't look too good right now. And hopefully my tricks up my sleeve will actually make this work. Mark my words, okay? Mark my words. Actually, how heavy is this? 100 grams. Okay. Apparently I did better back then. It's literally and figuratively not gonna fly. It's just too heavy. 100 grams is about double what a normal drone would be with these motors and propellers. So in other words, like at most around 50 grams total. So now I'm panicking because obviously I can't just cut the drone in half. The only way to not barbarically just cut the weight in half and achieve the goal is to redesign everything. And it was very painstaking to make the first one, but it's probably more painstaking to do all of this just so that the drone can spin half of the motors and not fly at all. And we're off to a great start because at least two of the motors work, which is not 4, but the drone is alive, let's say. I probably burnt one gate driver from soldering with too hot of a temperature, causing it to burn out before I even turned it on. Yeah, I'm gonna have to come up with some ideas for a better drone design. So just like Carl Fredrickson in Up, I'm going to have to throw a lot of things out if I want to get into the sky. So since the gate drivers are fried, I'm just gonna do away with it. And that means that I don't need to have a boost converter just to get the 10 volts needed for the gate drivers. The other thing that is pretty heavy is the perf board. Now you would think that is pretty important because it connects everything together, right? But I think we can get away with no perf board and just directly solder everything together and have a bajillion wires hanging around, just not secured anywhere. The next thing that actually has a lot of hot glue is the heavy frame. And it has, the cardboard, which is pretty light, but then it has the fork handles and an ungodly amount of hot glue. I'm gonna have to find a way to make a frame stiff enough, but much lighter. Goes to show just how amazing modern electronics are. And yes, I'm gonna start glazing PCBWay in this sponsorship segment. This PCB is smaller than the drone itself, and yet it can do so much more because it has a boost converter, an IMU, a microcontroller, motor driver circuitry, distance sensor, a USB, all of that within a few grams, which is about the weight of this singular ESP32 board. And typically I would design a PCB in KiCad and then have PCBWay make it for me, rather than slaving away trying to solder all the wires on my own that would have been embedded into a nice PCB anyway, and also more reliably. In fact, a simple board would cost me like 10 to 20 bucks, while this board, the most advanced I've ever made, costs $35 to manufacture. So what's the magic answer to cutting the weight in half? Popsicle sticks. They're light, they're thin, and they're stiff, okay? So I CAD the new frame to work with the sticks. I still plan on gluing everything together with hot glue because I guess hot glue is the best thing for this project. I'm guessing 5 grams, maybe? Ooh, 4. Much better. And now I'm gonna have to disassemble the electronics using something called a desoldering iron. Pliers win again. Let's go. To reassemble the electronics, I use a pin header to solder and mechanically mount the IMU in the right spot and connect it to the right pins on the ESP32. Okay. For the MOSFETs, I basically just took a chunk from the perf board which had the MOSFETs on it, so that I don't have to disassemble anything in that area. And this was very tedious because I had to use a knife to score the PCB for like 30 minutes. And then I just broke it with my bare hands. And then I assembled the rest of the electronics, also glued it to the frame with, again, hot glue. The ESP32 board actually serves as some extra rigidity because it's literally a piece of metal. I also added some bulk capacitors, as well as a 5-volt boost converter for the ESP32 to prevent the brain of the drone from cutting out under heavy loads. It's pretty instant. As you can hear. So everything's assembled with the propellers on, and now it's time to weigh the drone. So for 54 grams for the actual drone itself, add that on top, 65 grams. 65 grams, wow, that is actually quite an improvement. That's like, what, 35 grams that we just evaporated. As impressive as that is, it's not going to fly unless we maximize the software. This ESP32 actually has 2 brains, called cores. So I programmed one of them to handle the Wi-Fi connection while the other core handles the actual flying of the drone. That core needs to be very streamlined. The very microsecond that the IMU has new sensor data ready, it sends an interrupt signal to the ESP32 to start transferring data, filters it, and updates the motor outputs with a cascaded PID controller to react to the IMU data. This happens all before the IMU gets new data ready, in other words, within 1 millisecond. And this speed is very important. So let's say that this shows the gyro sensor on the IMU outputs. If we take samples fast enough, we can clearly connect the dots to recreate the true sensor output. But if we sample too slowly, connecting the dots seems to create a new, slower output signal that is incorrect, fake, or in other words called an alias. We don't want to process the alias. So that's why I try to have the highest bandwidth by having the IMU sensor sample at 1 kHz, every 1 millisecond, in other words. Every millisecond, we process the IMU data with a Kalman filter, and it essentially looks at the accelerometer and gyro of the IMU and combines the outputs of those to create clean data points to pass off to the cascaded PID controller. This controller has two parts. The first controls the angle that the drone is at, and based on how far the drone is from the desired angle, it passes a larger or smaller desired rotation speed to the second part, which tries to keep the drone spinning at that desired speed. And that's what cascaded means. One part feeds into the next, which should hopefully keep the drone stable. And finally, my janky Wi-Fi dashboard, which I use to send commands to the drone as a sort of controller. So let's hope all of these tricks I've learned over the years will pay off. I'm just gonna hold on to this, and then we just lean it, and we'll see what happens. Definitely reacting correctly. I can feel it. You should try. You seem so close. Come on. You got this. Balance it on. If I can balance it on my finger. No freaking way. Come on, guys, it's got to be ready, right? If I can balance it like this. I have deemed this flight worthy, and I guess we're gonna try and fly it now. Cut off a piece of Velcro right here. Oops. We're off, and then we're off. Too bad, so sad. This is definitely not. Oh man, is it too... Hopefully it doesn't go haywire. Okay. The pitching actually works here. My goodness me. It's doing something. Whoa! It just did a flip! It just did a flip, guys! No way. Okay. Let's pitch down a little bit more. Just trim it out. Gotta go higher. I'm gonna go higher. Yo! Yo! That's crazy. I just want to get a little bit higher, which might be a bad idea. It's literally flying at 30%. 30% throttle. Ooh, that's a hard landing. What if I just let it rip? Like, it just keeps flying forever and ever. And you know what? I'm just gonna let it rip. Hopefully it doesn't damage anything. Oh my goodness. Probably. Here we go. Oh no. That's unfortunate. Just put more hot glue on it, I guess. Maybe I should try it out here. No, that's not. Yes! Let's go. Where's that place? Oh! Oh man. I just, like, once it gets up in the air, I just need it to hover. Perfect. Let's go. How long is it? Oh boy. Man, that was a fun project. So ironically, the popsicle stick drone did better than my first ever drone with 3D printed parts. But if for some reason you want to make this abomination yourself, then I'll put a parts list in the description, and I might also make a YouTube video on that. And there's so much lightning and thunder right now. But anyways, yeah, I'll see you in the next one.